All right, we have two little mini topics today. So this video is going to include both of those. It shouldn't be very long though. So last time we talked about radians, and today we're going to talk about how to convert between radians and degrees. So sometimes as you have a degree measurement and you want to know how many radians that is, or vice versa. So when we want to convert, we use the conversion factor. It works with distances, times, temperatures. There's always some kind of conversion factor that you can use to convert between two different types of measurements. So for radians and degrees, the conversion factor that we use, it uses the fact that 180 degrees is exactly the same as pi radians. Those two rotations are exactly the same amount of rotation. So to convert angles, we can use these two conversion factors, either 180 over pi or pi over 180. So if we have a radian measurement and we would like to know how many degrees that is, here's our process. So we start with our angle. In this case, we're going to start with the angle 5 pi over 12. Now that's a radian measurement, and we want to know how many degrees that is. So since we're looking for a degree measurement, we're going to use 180 over pi as our conversion factor. And typically, the way I remember which conversion factor to use is that I try to just remember that the thing I want, the measurement I want, in this case degrees, is the one that is in the numerator. So if I multiply that, you might notice that the pi's cancel or reduce. And so what we're left with is basically we've got 5 multiplied by 180 and dividing by 12. And we can calculate that in our calculator. 5 times 180 divided by 12 is 75. So 5 pi over 12 radians is the same as 75 degrees. So let's try that one more time. We're going to convert 7 pi over 4 into degrees. So we start with that measurement that we have. And we're going to times that by the conversion factor, 180 degrees over pi. When we do that, those pi's reduce to 1. And so we have 7 times 180 divided by 4. This is the same as 315 degrees. In your calculator, you can type it in as 7 divided by 4 times 180, or as 7 times 180 divided by 4. You'll get the same answer either way, so you can type it in whichever way makes the most sense to your brain. All right, so that's converting from radians to degrees. Let's convert something interesting here. How many degrees is 2 radians? You know, this does not say 2 pi radians, so be careful. This is exactly 2 radians. So if I want to convert this, I write the angle that I have, in this case 2 radians. I times that by 180 over pi. It's the same conversion factor. I want my answer to be in degrees. When we do this, you might notice that there is no pi to reduce. That's fine. It just means my original angle wasn't in terms of pi. It's fine. So we still can just calculate this. We'll type into our calculator 2 times 180 divided by pi. And we find that it is about 114.6 degrees. Now, this makes sense. If you remember yesterday, we talked about how 1 radian is about 57.3 degrees. So it makes sense that 2 radians would be twice that, about 114.6 degrees. So be careful. Don't assume there's a pi if there's not one. All right, so now we're going to go the other direction. What if I have an angle that's measured in degrees and I want to know how many radians it is? Well, it works the same way pretty much, except we want our answer in radians, so we use this conversion factor, pi over 180. So we write our original angle, in this case 210 degrees, and we want to multiply that by pi over 180, or conversion factor. Okay, well, if we type that into our calculator as is, 210 times pi divided by 180, it's going to give us a decimal approximation for this answer, which would be okay, except we don't really love decimals. So what you want to do actually is just focus on the numbers and leave the pi. I mean, the pi is going to be a part of our answer. Like in a minute ago, we had a 7 pi over 4, we want to leave that pi. So we just want to figure out what fraction 210 over 180 is and reduce that fraction. And what we end up getting is 7 pi over 6. So let me tell you how you can get that from your calculator if you're using a TI-84 graphing calculator. You can type in that 210 over 180, and you could reduce this fraction by hand, of course. Sometimes we need speed on our side, especially when we're taking the ACT or other things like that. And then in your calculator, there's a button that says Math. And when you hit that Math button, the first choice looks like this. That means convert to fraction. So if you do 210 divided by 180 and convert it to a fraction, it gives you this 7 over 6 reduced fraction. So that's a really fast way to just reduce that fraction and get your radian answer. And again, leave the pi. The pi doesn't disappear. We just wanted this exact answer instead of a decimal approximation. So let's try one more of those. Convert 300 degrees into radians. So we take our measurement, 300 degrees. We're going to times it by pi over 180. And we are just going to focus on the numbers so that we can reduce that fraction. 300 over 180 is the same fraction as 5 over 3. So our answer is 5 pi over 3. Don't lose the pi. Okay, in your notes, if you have the notes packet, there's some to practice. I'll post solutions to those practice problems on my website so you can check your work. All right, our second topic for the day is a review of special right triangles. As we're working towards building the unit circle, one of the things that we are going to utilize are special right triangles. You studied these a little bit last year in Math 2, so we're just reviewing them this year so that we can utilize them. Also a good topic to review before the ACT. So special right triangles. There are two special right triangles. You might remember that one of them is the 45, 45, 90 triangle. In a 45, 45, 90 triangle, the hypotenuse is always root 2 times as long as each leg. So the two legs, it's an isosceles triangle, so the two legs are exactly the same, and the hypotenuse is that length times the square root of 2. Now this special right triangle pattern, you know, the whole purpose for it is really just to make us faster and let us focus on other things happening in our mathematics so we can find these lengths really quickly. We're going to do a few practices with this pattern and then we'll talk about the other pattern. So our first triangle here is a 45, 45, 90 triangle, and it has a leg that has length 6. So this other leg must also be length 6, and the hypotenuse would be 6 root 2. If you know the length of the leg, this is an isosceles triangle, so these must both be 45 degrees. If you know that length is 4 root 2, sometimes people just think a 4 root 2 would just go with a 4, but remember to think about what you have, and in this case we have the legs. So to find the hypotenuse, we take that length and we multiply it by root 2. So root 2 times root 2 is just 2, so our length is 4 times 2, which is 8, is the length of the hypotenuse. Find the length of the legs now. Well, if I know the hypotenuse is 9 root 2, the legs must have been 9. If you know the hypotenuse, the way to find the legs is to divide by root 2. So in this case, it just reduces to 9. In this triangle, again, we know the length of the hypotenuse, so to find the length of the leg, we I have to divide by root 2. If we rationalize that, we end up with 12 root 2 over 2, and that reduces to 6 root 2. So the length of our two legs is 6 root 2. One more. If we know the leg is 2 root 2, to find the hypotenuse, we multiply by root 2. So this will be 2 root 2 root 2. That's kind of fun. That's the same as 2 times 2, which is 4. So this has a hypotenuse of 4. So when you're working with 45, 45, 90 triangles, just remember, if you're going to the hypotenuse, if you're going to the longer side, you multiply by root 2. If you're going the other direction, you have to divide by root 2. Also, as you're doing the ACT or as you're working on the homework assignment, remember that a 45, 45, 90 degree triangle is a square cut in half. So oftentimes if you have problems involving squares and diagonals of squares, you can use these triangle, the 45, 45, 90 triangle relationship. Okay, the other special right triangle is the 30, 60, 90 triangle. This one is a little bit trickier to work with. I have an easier time remembering it if I think of a 30, 60, 90 triangle. Let's see, I'll draw it in the same orientation. If I think of it as half of an equilateral triangle, because it is half of an equilateral triangle. But when I remember that, whoops, well, I guess I get to draw it again. When I remember that it's half, it helps me to remember that if this is x, this distance here, that the hypotenuse is 2x. So I always picture in my mind that equilateral triangle, and then I can remember that the other one, which is the height of the equilateral triangle, is x root 3. So the hypotenuse is twice as long as the short leg. The long leg is root 3 times as long. This definitely is a more challenging pattern than the 45, 45, 90 pattern. But if you practice it a few times, you'll get the hang of it. So in this triangle, we have the hypotenuse is 8. So again, sometimes it helps me if I just picture that equilateral triangle. That helps me find and remember that this one's going to be 4. And then the other leg will be 4 root 3. This time it's the height we have. So again, if I picture that equilateral triangle, if I can find x, I know y is just twice as long. Well, if I'm going in this direction, I multiply by root 3. So if I'm going the other way, I have to divide by root 3. So x is 8 over root 3. So if we rationalize that, we get 8 root 3 over 3, and that one can't be simplified anymore. So that's our solution for x. Now for y, we just need to double it. So y would be 16 root 3 over 3. Sometimes people try to turn that into a 16 root 3 over 6. So be careful there. I think the easiest way to realize why it's not that is to think about that what you're multiplying by here is 2 over 1. So the 16 root 3 is for the numerator, but the denominator does not get multiplied by 2. It's still just a 3. So here's our solution for y. Okay, another couple. Find the value of the variable. So in this first triangle, we're looking for the value of x. Well, we've got the short leg. The hypotenuse would be twice that, 4 root 3. The height of the triangle, or the long leg here, is going to be 2 root 3 root 3. Well, root 3 times root 3 is 3. So this is the same as 2 times 3, which is 6. All right, we've got one more. We have a 30, 60, 90 triangle here. We know that the short leg of the triangle is 6. We know that the hypotenuse is 12. We want to know what the height of the triangle is. Well, it must be 6 root 3 according to our pattern. Okay, so that's it. I will post solutions to the homework assignment. I'll try to get a PDF of the homework assignment up as well in case you need to print it because you've been absent. We will actually be working on some ACT prep next time in class, and then we'll pick up our unit again after that.